Okay guys, let's get started with this last video on determining the orders of reactions. I decided to do a pretty long video on this one because I want to really go through everything that we discussed, from rate laws. We actually didn't go over an example of determining the value of k, and we also didn't go over, using everything and like why are we even considering this. So what I want to do now is just do a comprehensive problem, going over everything we've gone over in the last two videos. So I encourage you, hopefully by this point, you are watching this video with some, some practice into these problems, and I hope that at least anytime you're watching these videos, you attempt the problems before you watch. Because if you do that, you're gonna get a lot more value out of these when you are, alongside. So let's get through this problem. So I'm gonna go relatively fast because it's gonna be a long video otherwise, and hopefully by this time you're a little more fluent in the topic. So let's get started. So in A, we determine the rate law of the reaction. So to do that, let's write what the rate law is and what I don't know currently. So the rate law is going to be equal to my K constant, my concentration of A to the M power, that's going to be my order, and then I have the B here, that's my constant, that other reactant, raised to the nth power. That's my general rate law right now. But what they want in this particular case is M and N for part A. So let's do this. So how do I determine the rate order for A? Well, let's find a reaction where B is held constant and A is changing. So it looks like to me that we can analyze equation 1 and equation 3. Let's take a look. So let's look at a reactant B. So reactant B was 1.3 to 1.3, so that's the same. So we can use this one because because reactant A is changing, but B is held constant. So let's take a look. So let's get a generalized view. And then that's my rate change here. So, all right. So by what factor did A change? So 3.70 over 1.85 is equal to the nth power is equal to 6.75 over 3.35. I'm eliminating the exponents that we see here because if I divide them, they will cancel each other out. That's why I'm doing that. So what do we get? 3.70 divided by 1.85. That gives me 2. So that's 2 to the nth power is equal to 6.75 over 3.35. 6.75 over 3.35. And that's equal to 2.0. So my M must be 1 in this case because 2 to the 1th power gives me 2. So I know what my M is. Let's find out what our N is for B. So how do we do that? Find a reaction where A is held constant and B is not. So that's going to be equation 1 comparing to equation 2. So let's do that. So I'm going to get rid of these red and everything here. I'm going to be analyzing this equation and this equation because reactant A was held constant, whereas B was doubled. So what's my order? That's going to be 2.66, or rather 0.266 over 0.133. That's clearly 2, but I'll write it anyway. 0.266 over 0.133 to the mth power. Sorry, it's going to be n power. It doesn't really matter, but to be consistent. And let's do it. So it's going to be 1.35 over, so actually this is different though, see, because it's times 10 to the negative 3. So I'm going to say times 10 negative 3, and then this is going to be 3.35 times 10 to the negative 4. So let's do that. So 0.266 over 0.133, that's just going to be 2 to the n is equal to my ratio here. So that's going to be 1.35 times 10 to the negative 3 over 3.35 times 10 to the negative 4. And the answer I get there is 4. So to what exponent does 2 need to be raised to give me 4? So n must be equal to 2 in this case. So I have my m and I have my n. So my overall rate law in this case, I'm going to do it in a different color. My overall rate law is going to be rate is equal to k A to the 1, B to the 2. So that's for part A. So pretty simple. I would expect something like this on the exam, to be honest. The previous example we went over in the last video was a little tough because it is a lot of algebra, but this is a little more representative, I think, of what you might see. So it's pretty comprehensive too, because it makes us do a lot of other stuff too. So let's go for part B. Calculate the value of K for this reaction. Well, to do that, what I want you to do is pick any row from this data set. So what I'm going to say is let's just use row 1 here. And we're going to literally plug in our values for everything in this rate law and solve for the unknown, which is going to be K in this case. So to do that, since we're using row 1, my rate is going to be 3.35. So I'm just going to write it again. And that's B squared. This is what we found out in part A. So plugging in row 1, my rate is 3.35 times 10 to the negative 4, empty brackets, is equal to K. And A in this case, the initial rate for A was 0.185. And the initial rate for B was 0.133. Now, notice that A in our rate law has an exponent of 1, but B has an exponent of 2, so I need to square this 0.133 that we see here. I can then divide both sides by 0.185 times 0.133 squared, and do the same thing over here. What I'm left with is that K is equal to, well, if I get the ratio, it's going to be 3.35 times 10 to the negative 4 over 1.185 times 0.133 squared. Sorry, my writing got kind of bad at the end. 0.133 squared. So what does my K equal? My K equals the ratio of 3.35 times 10 to the negative 4 over 0.185 times 0.133. I'm going to square that number. My K constant is going to be equal to 0.1023. That's equal to K. Okay, so let's just see what we did, just to double check that we did everything correct. So my K constant, we determined that, so we picked any row from our data set. And because we know the orders of A and B, we can now solve for K. Because we had our rate law written right here, our rate law was written. So I quite literally plugged in the value for the rate, which is right here, 3.35. I plugged it in. I just don't know what K is, but I know that the starting amount for A was this 0.185, and for B was this 0.133. Now, all I did then was, because I don't know what K is, I just divided both sides by 0.185 and 0.133 squared, and I was able to solve for my K. Very simple. So now that K is going to be the same for all 4 of our experiments, and that is key. So that's super key. Same for all experiments at the same temperature. Well, because K is actually concerns temperature and a lot of other things, which we'll go over later in different videos. But for right now, just remember that your K constant is the same for all of these experiments that you see. And we can exploit that, because in part C, we're determining the rate of experiment 4, which we don't know. But we can know if we use our rate expression, our rate law, which is why this is so helpful. Our rate, we found to be the K of A and B squared. We do know what our value for K is now. So that's equal to, our value for K is 0.1023. Our value for A, let's pick, well, we have to pick from experiment 4. So what was our starting amount for experiment 4? That was the 0.370. For B, we're going to pick the 0.266. So 0.370 and for B was 0.266, and that was going to be squared. And that's pretty much it. So we have all of our values here, so we can solve for the rate for experiment 4. And that's why this is so useful. If you know the orders of your reactants, and you know your K constant, you can quite literally, through mathematics, determine how much faster your rate will be without even doing it to a reasonable degree. So once we're done, we can just submit this. So let's see, let's plug this into the calculator. 0.1023 times 0.370 times 0.266. Let's square that number, and I'm left with a new rate. So that rate 4, is going to be equal to 2.67 times 10 to the negative 3 molar per second. Great. And we solved our answers. So we just went through a lot in this video, but it's good because this covered pretty much everything we've learned in the last 2 videos or so. So this definitely exploited the method of initial rates to determine the orders. So if you're given a question like this and you don't know what that is, your very first instinct should be, I need to determine what my rate orders are. I'm given a data set, I have the ability to do this, so let's do it. So solve for it, and once you know that, once you know your orders of your reactants, you can solve for the K, or the rate constant for your reaction. And the way we did that, we picked any row from our data set that we knew all the values for, and then we just solved for K, because it was the only unknown in our equation. That K, we said, is the same for all experiments at the same temperature. So that means then we were able to exploit that fact to solve for the rate for experiment 4 without even having done it. So this was a pretty cool problem. I hope it was helpful in determining rate orders and whatnot. We're going to continue with some integrated rate law problems in the next video. And I hope these are helpful, and study hard.